Alright everybody, this is the last section we're going to do in Chapter 5. It's about exponential growth and decay. So let's just start with what exponential growth looks like. Okay, exponential growth comes from the function that's generally like y equals a times e to the bx. Okay, and the conditions here are that a and b both have to be positive. Now, exponential decay is the same idea. It's y equals a times e to the bx, but now a is positive and b is negative. Okay? So anytime you see a function with these conditions met, you know that it's either going to be exponential growth or decay. Now, in particular, we're going to be very interested in working with the growth law, which comes from both of these two equations. The growth law is n equals n naught e to the k times t. And now this variable n represents final amount or population. This is obviously initial amount or population. This k here is going to be a growth or decay constant. And then t is obviously time. Okay, so these variables are defined as we did here. And now, actually, if you take out your packets and the section that says exponential growth and decay, if you want, you guys can fill this in later on, or you don't have to since we have it in your notes now. But let's look at example 1 together. And this kind of takes you through the stuff that you need to do when you're dealing with the exponential growth law. All right, so for the first example, let's see. So in case you haven't seen what we're talking about, it says that we have a start of an experiment. Initially 1,200 bacteria were present, so I'm just going to write down what we know. So n naught is going to be 1,200. 4 hours later, so when t equals 4, now the population is 2,200. Okay, and from that, we should be able to find the general growth law, and we can use it to find any information we need. How long it'll take to double, how long it'll take to triple, how much there will be in 7 hours. I mean, we can find anything as long as we have the growth law. Now, in order to do that, the first thing we're going to have to do, if you haven't seen Part A, is find the growth constant. Or decay, if it was a decay question. And you do that by just plugging in what we know. So we know that to reach 2,200 bacteria, we started with 1,200, so that's our n naught. We have E. K is what we're trying to find, and this happened when we had, this happened 4 hours in. Okay, so now we just solve the equation. So if you divide both sides by 1,200, you get 11/6 equals e to the 4k. And now if we put this in log form, this is log base e of 11/6 equals 4k. And we know log base e is the same thing as natural log of 11/6. We're going to divide everything by 4, and now this is your growth constant. So that's part A. Now my advice is to store this. Store into the calculator. And if you forgot how to do that, you press the STO button, and then you assign a variable. I'll probably put it in K. Okay. You assign a variable and you store it in there. The idea is now you don't have to type all this in later on when we're doing the calculations. For instance, part B. How many bacteria are present? 3 hours. So how many bacteria after 3. So now we just say, well, I don't know my final amount after 3 hours, but I know that we still start with 1200. E is E, and now K, I'm going to color it differently because we're going to plug it in here. We actually know what it is, I'm just not going to write it out. And then we're going to plug in 3. Okay, so on the calculator, you're just going to type in 1200 E, and either you store this into a constant K or you type it all in again. Okay, and to save time, I'm not going to do the calculations because I've already worked them out, but you should get about 1890.66. So we'll say about 1891 bacteria. Okay? Let's see. Part C, when will the population reach the 3,000? So you just do 3,000 for the final amount. We're still starting with 1,200, same experiment. We just don't know how long it's going to take to reach 3,000. So we do 1,200 e to the k, which we now know. And now t, that's what I'm trying to solve for. Okay, so I don't know what that t value is, but we're going to start off the same way. Divide by 1,200 on both sides to try to get t alone. So we get 15/6 when you reduce the fraction, e to the k times t. Since we're stuck, now we put it in log form. So this is natural log of 15/6 equals equals k times t. Again, we want to figure out what t is, so we're going to divide everything by k. And again, this should already be stored in the calculator. If you didn't store it, then you're going to have to just type in natural log of 11/6 divided by 4. That's what k equals from before. And when you do that, you get that t is about 6.05 hours. Okay, so there's an example of exponential growth. We'll do a decay example, but before we do that, I want to define half-life. So actually, if you turn the page in your packet, you can come on in. I'm just finishing my video. If you go to the half-life section, you'll see some spaces there. Go ahead and write down the definition, which is the time required for half of a given substance. And actually, this could be anything. But whatever amount we start with, it's the time that's necessary in order to only have half left. So the time required for half of a given substance to disintegrate. Typically, you'll see these problems with like radioactive substances and stuff like that. Okay, so final example. If you actually look, let's look at example 4 in the packet. You know what? Never mind. Let's do example 3. Okay, so if you read through it real quickly, you have 2 grams of a substance initially. The half-life is equal to 5 days. And the question is, how much is left after 30? Okay, so we can do that using that growth law that we've been talking about. Plugging in that we know initial amount is 2 grams, so N naught is 2. We have E, we have K. And now here's what I know. I know that the half-life is 5 days, so when I plug 5 in for T, this initial amount, which was 2 grams, is going to get cut in half. So the final equation will be 1 equals 2 e to the k times 5. And now, in order to answer the question, how much is left after 30, first you have to find the growth constant, just like in the other example. So we're going to find k, so we divide by 2. And now we switch it to log form, so natural log of a half is going to equal k times 5. And then if you divide by 5, there's your growth constant, or in this case, your decay constant. Again, I would just store this in the calculator. So now you have natural log of 1/2 divided by 5. That's your new value for k. And now to finish the problem, we're interested after 30 days how much is left. So we don't know the final amount. We're going to leave that as n. We still start with 2 grams. K we now know. So we know this value. We're using it from before. And now we're just changing the time from 30 to 5 days. So this is what you type in the calculator. 2 times e. You've stored in natural log of a half divided by 5 for k. Multiply it by 30. And we get that this should be about 0.03125 grams. So there's not much left. Alright, so this is the basic idea for growth and decay. You'll work on some of the nuances in class when you work on the packet. See you guys later.